All right, so we've been going through kind of exploring the code that was already out there. I've been adding in some other things just to remind ourselves to remind me what we talked about last class. We were messing around with worker bee. We talked about, let's see, did I not save this? Well, that's okay. We'll just write it again real quick. So we had a second constructor for worker bee that only took in a string name. And this constructor then called upon one of the other constructors. So if you're going to use another constructor to leverage the work for you, you use the keyword this. We'll pass it the name and then go ahead and pass it null because this guy didn't have a friend. If you remember, that's how we were referring to it last time. So we have two different ways of creating worker bees. One, just give it a name and he goes ahead and creates it using the other constructor, passing null in for the worker bee. Or we can call the normal constructor that takes a name and the worker bee that this guy knows about. Let me save that so I don't lose that again. So back here, the original code I'd given you has worker bee T1, passed in Mike and null. So right now we're only leveraging one of those constructors because we just invented the other one. So now I can take out that version of it and say, well, worker bee T1, when he's initially built, he's built with just the name. And then under the hood, it sets his friend as null because he doesn't have one yet. Worker BT2, we do have a friend to pass it, so we send the name as well as the other worker B we want him to know about. We tell them both to start. This should give us equivalent working code to what we had um, uh, at the end of, well, leading into the homework, even though um, we've done a little bit more. So I asked in class last time if we wanted T1 to be aware of T2, then we'd have to give a setter for that guy. So here in worker B, because the other thread is a private variable, in order to set a private variable from an external entity, we have to give write privileges, a setter. So maybe we do something like public void set set the other thread, name it something like that. And this guy will take in a worker bee, the other thread, and we'll set this dot the other thread equal to the other thread. So now we have a setter that can internally access this dot the other thread, yet he gives us external access through this public method for somebody else to send in a thread that we then set right here. This then allows us to come out here to driver, and after we've created T2, we can say T1.set. You know what? I'm going to just copy that. T2 dot set the other thread to T1. I'm lying. T1 dot set the other thread to T2. So when we built T1, T2 didn't exist yet, so we weren't able to allow him to know about T2. Then we built T2. Now we're going back and letting T1 know about T2. Still not leveraging that. Just now our instances of our worker bees have some additional knowledge that we're not necessarily using quite yet. All right. And then we tell it to start. Nothing else should have changed. It just does whatever it did before, which isn't quite, you know, what we wanted out of the homework. So what we wanted out of the homework is for there to be some communication between these two threads. And what we want to do is we want to stumble upon, let's call it kind of a hacked communication first, and then go and look at, well, probably the Java, some microsystems people, when they wrote Java and they created threads, they probably built in some sort of way for these threads to communicate with each other, right? We haven't learned about that yet. So let's see if we can kind of massage this to make it work based on things we do already know. All right. So let's start off with doing a little bit of experiment before we get down to the what we want this thing to actually finally accomplish with the, what is it, like the ping pong pong ping ping, whatever that dealio. All right, you'll help me remember that when we get to it. But in any case, if I'm inside worker bee and when I go to run, just to remind ourselves what run does, right now it says if you don't have a friend, if you're, well, this says you do have a friend. If the other thread is not equal to null, you do have a friend, then you're going to wait for that guy. We'll wait for that other thread to do whatever he's going to do. In this case, it's his run method ends, but there's a little bit of a timing thing somebody asked about after class last time. I mentioned this in class when we first introduced threads, something called a race condition. We'll be talking about that a little bit more as we get into this. These are more operating system type concepts, but we'll see programmatically how we can handle this, how Java's given us some tools to manage this idea of race conditions. Sometimes you'll, if you're looking at documentation, when something says that it is thread safe, if you see that phrase when you're looking at documentation for something or you're looking at a tutorial, if something is listed as thread safe, it means it's using the internal mechanisms to protect two separate threads from accessing the same thing at the same time. However, it magically accomplishes thread safety behind the scenes, it's already doing it for you. But that's what that phrase means, is thread safe says we protect you against threads bumping into each other as you're trying to solve stuff. And that'll make more sense as we go through here. Okay, so now, good. They both, well, so they're two different channels. So all operating systems have one input channel, which is called system.in. And then they have typically, if they're based on POSIX, so some standard operating system thing, they have two output channels, system out and system error. By default, both of them will show up on the screen from a human being's perspective. But technically, system out and system error are kind of like two different pipes. And that allows you, if you are a person who's writing a piece of software, if you want to keep a log file of like the errors that your program creates, you might purposely, when your program runs, redirect anything that's on the system.err channel to go to some file that keeps track of errors that you bumped into. Whereas you probably don't want to store every single textual output from your entire program in this file that is meant to be kind of a convenience location for you to go and look at what just went wrong when my program crashed, something like that. So it allows us to separate kind of good stuff from bad stuff if we care, if we're interested. And that's not a Java thing. This is a old school Unix operating system thing that just hasn't died off type thing. That in C++, we have C out, we also have C error, CEE or CERR, I think is what it is. It exists in basically every language. All right. So as it stands right now, these guys are waiting on each other or whatever. But now, as we have it written, everybody has a friend, right? So at the end of our line 15 right here, T1 knows about T2, T2 knows about T1. So everybody has a counterpart worker thread that they know about. So kind of the old logic of what I originally gave you now is kind of broken because nobody will ever have a null friend. So with that in mind, let's just go ahead and let's gut all of this so we can start working towards a bigger solution. All right, so now when both threads start, going back to driver here, so these two lines right here, remember that's calling the magical function given to us by the thread class that knows how to talk to the operating system to spin off a thread. So when both threads start, what ultimately happens is they both call their run method inside of a threaded environment that was magically created for them. And right now, neither of them do anything. So if we were to run this program, it has no output. Oof, works perfectly. All right. So now what we want to do is we want to try to create some banter between these two threads. Have them at least take turns doing something. All right. So because we don't want to let our run method accidentally end, what we're going to do is we're going to do something that usually might not make tons of sense. We're going to say we want to do something forever. So now we have an infinite loop inside of our run method, which means our threads will never die without some additional intervention on our from a logical perspective. All right. So what we can do is we can say system.out.println this dot name or something like that, where now what happens is both threads just are constantly trying to print their name out to the screen, not taking turns, not doing anything. So we're at the mercy of how the operating system is scheduling these threads. Okay, those are things that are out of our control. Okay, this is just free for all. They're all competing for the same processor, potentially the same single core on that processor, depending on how the default Java virtual machine is interacting with the operating system. But anyway you cut it, this is out of our control. Both threads are running. They're both in an infinite loop. They're both trying to print out this dot name. One of the threads' name is Mike. The other thread's name was what, Dave? Yep, we got Mike and Dave. So we should see some array of Mikes and Daves to the screen. Sometimes we'll see several Mikes in a row. Sometimes we'll see several Daves in a row, because that's when they got CPU time, and that's when they ended up getting their chance to output something to the screen. So I'll go ahead and run that. I'll just stop it, and we can, because remember, it's an infinite loop. That was never going to stop on its own. Does it let me still look at what was going down? Oh, perfect. It doesn't. But hopefully we saw that you did have a, well, you get the point. Sometimes there were several Mikes in a row. Sometimes there were several Daves in a row. No rhyme or reason. What we want to do is maybe start off with creating a situation where it does alternate between Mike and Dave, just to kind of get control over this situation. All right. Now, we want to try to do this. I know, I graded all the homework already, and I know several of you went and did some searching and saw that, you can tell threads to go to sleep. Threads can notify each other, stuff like that. You kind of use some of the built-in thread stuff, which is okay. But my intention was, although I did teach you how to read documentation, so that was free for all. You can do that if you wanted. But my intention was for you to kind of like try to MacGyver a solution, right? It's like, okay, here's my pile of tools I have here. He's taught me how to just the basics of threads and just said go. So what do I do with this? So let's try to think about from last semester, we needed multiple objects to communicate with each other. And we learned about something called a design pattern. I don't remember if it made it into the notes or we just said it out loud. Anybody remember what design patterns are? Let's start off with this. Does it sound familiar at all? Did I mention that phrase? Just keep in mind, I forget what happened yesterday. That's why I had to look at just what went down. So let's assume no, but probably yes. I probably said it in one of my rants where I go off topic and twist and turn and do whatever. So a design pattern is a proposed good solution to a common problem. All right. And typically when I first introduce design patterns, I might say something along the lines of like, what's the best way to make a peanut butter and jelly? Everybody might have their technique. Some people, they might use a knife and they evenly spread the peanut butter or whatever. They do the job. I mean, I don't do that. I take a spoon, I just put a big old glob of peanut butter on there, and then I put a bunch of jelly on there, and I smash the bread together, and that's what spreads it all out. And then you basically eat the whole thing in one bite, 3 bites. That's my approach. So from my perspective, that if I were to give you a tutorial on making if I were to create a design pattern for making a peanut butter and jelly, it usually has to have a fancy name. So we'll name it Mike's PB&J, something like that. They get cooler than that when you get into coding stuff. But what I'm doing is that I'm selling that to you as the best way of making a peanut butter and jelly, where you might have your own version of how to make a peanut butter and jelly. So take this idea of a good solution and a common problem with a grain of salt. Okay. There's this idea among academics when it comes to like research and stuff called publish or perish, where you're supposed to go to conferences and write research documents and stuff like that. Design patterns are excellent cop-outs for that because nothing prevents us from coming up with a funky name for something, taking some problem, whether it's common by normal people standards or not, and just propose a solution, whether it's actually that good or not. And just say, this is a proposed good solution for that problem. And then at the end of your paper, you just say, yeah, it wasn't as good as I thought. Publication. Check mark. All right. But in general, that's what this concept of a design pattern is. Now, one of our design patterns that I want to focus on right here is something called a singleton. Does that sound familiar to you? Okay, so singleton, this basically says it is a good idea to store information that needs to be accessed by multiple things in a single place. So in the real life example would be, let's say you live in an apartment with 3 roommates and you all share a car. You might decide to keep the keys to the car in this drawer, right? And whenever somebody needs the car, they check the drawer to see if the car is available. If it's available, now not all singletons will necessarily work this way because they might say, hey, this information is always accessible. But with this example, when I grab the keys to go use the car, no longer are the keys there. So if somebody else tries to come and get the car they go to the drawer, they see that the keys are not there, they're out of luck. They got to wait for the keys to magically reappear for them to go take the car. But the idea is we picked a centralized place to have information. If you want to have something a little bit more like the traditional use of a singleton, it might be like you might have a calendar on the fridge in the kitchen where all of you have the ability to write stuff on that calendar, sending notes to each other or something like that. So at any point in time, any of the roommates can come and check this central location to kind of see what's going on. See who's at work today until what time, that kind of stuff. So it doesn't matter how many of them are, how often you come back. It's centrally located regardless of who you are. All right. So it's not like one roommate is remembering that stuff and you always have to go to them to ask. We store it on the fridge. All the roommates have access to that fridge. All right. So that's what a singleton is. The reality is it's just a class, a normal everyday class. And the way we write it is leveraging our knowledge of static versus non-static. So this is nothing new. So let's go ahead and create a new file. And I usually will name my generic singleton something like core. I don't know why, just the core of my program or something like that. So I'm going to name that guy core.java. Here, I'll just have it with a capital C so we don't have things looking too quirky. All right. And this file is going to be a normal class, public class core. All right. Now, I do not intend to create instances of this class, which means I don't need to have instance non-static fields. I don't have to have constructors. This guy, remember when we introduced the character class where we can pass chars to it? It's character, like to convert a char to uppercase. It's character dot to uppercase. You can kind of think of that character class as somewhat fulfilling the role of a singleton. When you need to do things to chars, you go to this one place that you always have access to no matter what part of your program you're in, because the character class is part of the core Java library. So now you don't have to import anything special. You just say character dot to uppercase, and you throw it a char, and it gives you the uppercase version of that back. Okay, it's a centralized tool that everybody has access to. So inside here, I'm creating my own version of that. So maybe I'll create they don't have to be public, but we'll just keep we won't rely on something being just the default, which is what's called friend or package level in Java. But we'll say public. Let's call this guy, and it'll be an int. And let's just call it public static int count. All right. And we'll start this guy off at 0. All right. So now we have just a variable. Now, how would I access? So if you see this code right here, and I go back to my worker bee, and I want to, instead of printing out just my name, I also want to print out the value of count. How do I access this variable based on what you see right there? So we're looking at the definition of this class and that variable based on what we know about whether things are static or non-static and how we call those things differently. How do we access that value of count? If I wanted to print out that value of count over here. What do you think? Nothing? We got nothing? Good. Well, tell me what that means. If I'm in here. Well, let me bring up Java character class. This would be one of those examples where the second I interjected the word singleton, we got intimidated. Okay, nothing special about this. Here's the character class. Let's take a step back a little bit. We're going to scroll down, and we're going to go down to our two uppercase function. All right. So down here is our two uppercase function. Functions, fields, they're the same thing. Just fields are just values. They're just variables. Functions are methods that have parameter lists that may or may not take inputs. Okay, but the way we call them will be the same. So if I go down to two uppercase here, I could have stopped at two lowercase, I guess. Uppercase right here. So if I go down to this guy and I ask you, I say, okay, there exists a character class that has all this crap in it. And one of the things it has is a method called two uppercase that takes a char as a parameter, and it is a static method that returns a char. And I ask you, how do you call this method? What would you say? How do we call static methods as opposed to non-static methods is the question I'm asking. Go ahead.
The name of the class.
Call it with the name of the class. This is a static method. Therefore, we call it using the name of the class in which this method was defined. This method was defined inside of a class called character. So we would say character dot to uppercase, and then pass it the char we want to convert to uppercase. All right, we're good with that. Let's go back to our code. We're looking at some documentation we just invented. Instead of this class being called character, we happen to call this guy core. And inside here, there is exactly one thing. There is a static field called count. How would I access that static field called count from outside this class? Go ahead. Core.count. You access static fields or static methods, any static member of a class, you access it using the name of the class in which that member was defined. Static count was defined inside of a class called core, so we would access it by saying core dot count. Like that. Make sense? We're in worker B. Core.java lives in the same directory. We have access to that class. I want to access the count variable that lives in there. It's a static variable, so I don't need to create an instance of core, which is good because I didn't write a constructor. We still got one that has no parameters, so I could create an instance. We just don't have any instance stuff to call upon, so it would be a waste of time. But we have a static field in here called count, and I can call it from another class by just saying core, name of the class, dot count. So if I run this code right now, it's just going to alternate, well, not alternate, it's going to be a bunch of Mikes, a bunch of Daves, and it's going to have 0 after every single one of them, right? Because we're not changing count, we're just reading from count. So go back to here, hit run. We should see some zeros flickering across the screen there. All right, we're good with that? All right, well now, what if I want each of these threads to print the current version of count and then modify count? Go ahead. Yep. So here in worker B, maybe after we print it, yep, so we'd say core.count is equal to core.count plus 1. Or we could have said core.count plus plus if we wanted to. That means the same thing. This would allow us to jump by 2, 3, 10, whatever we wanted, but same thing. All right, so core.count equals core.count plus 1. Now remember, we have 2 separate threads running at the same time, out of our control same time, right? You know, even though this computer has, I don't remember how many, I think there's maybe 30 cores on my CPU on this computer. But for all I know, the Java virtual machine's default is using 1 or 2 of them, unless I give it a command line argument to expand its horizons. It also limits the amount of RAM you have access to, so you don't bring your computer to its knees. But point is, it's mostly out of our control. We're at the mercy of however the Java virtual machine is scheduling these threads, which effectively means we might have Mike add 1 to count a whole bunch of times in a row before, you know, Dave even gets to it. Right. But at the very least, we are changing the value of count now. And as our threads are both running, however they're being scheduled, at any point in time, they're going to be grabbing the current value of count. All right. So let's go ahead and print this. Now we should see at least count changing some values. All right. So at this point, we have a centralized variable, just one of them right now, that both threads have access to and both threads are manipulating in some way. All right. Free abandon. It's just a free for all, whoever grabs it. That's what a race condition is in operating systems. So, you know, we basically have a single thing, and what we would need to do from an operating system perspective is if we wanted to protect that single resource, that shared resource, which is just an integer in this case, we would have to kind of put a bouncer at the door. You know, the bouncer might say, how many people are allowed in at any point in time? And if we want to have exclusive access to this variable, where if anybody is going to make a change to this variable, in order to read it and change it, that has to happen all at a single time. And we lock the door in between users. All right. There is something in operating systems. Let's just get it on a slide to kind of close this thing. Let's call this race conditions. Now, this is something that super important to understand, super important to know it's there, but not something I'm going to test you on because it's a concept from operating systems, but it's something that we are experiencing here in coding. So I want you to know what's actually happening behind the hood, but it's not something that I'm testing you on for knowledge from this class. But a race condition basically says more than one process or thread is trying to access I'll call it access the same resource at roughly, here, let's put that in quotes, at roughly, whatever that means, the same time. And there is little control over who gets that access, which could mean in a bad situation that they both access it. So let's assume that there's like a database and there is a password that you're updating the password, but two different people are trying to update the same password. And let's just say that they've timed it and they basically both hit submit at the same time. So now as the internet flows and all this stuff is going, one of them is going to arrive at that thing barely before the other one, let's say. So what's going to happen is he's going to grab the resource, but if we're not protecting that resource, the other guy's also going to grab the resource. So now you have two people trying to change the same piece of information on a single resource at the same time. What change is going to be actually realized permanently? It's going to be whoever wrote to it last. So if the first thread that got access to it changed the password to Woot, and the other one then who got access to it second changed the password to LOL, LOL's the one that will stick, the last one that was written to memory. And we might want to have control over things like that not happening so that we don't have somebody who changes their password, then goes to try to log in, and somewhere in the middle between when they changed it and when they go to log in, somebody else has changed that value. That's what a race condition is. It's important for some problems. It's not that important for other things. If you're reading from a value that doesn't change, if you're not modifying the value, like when we had count was 0, you don't have to protect it. You can grab the 0 from that guy all day long. Doesn't matter. But if you're going to start making changes to it and you expect those changes to be experienced accurately by the other folks trying to access that resource, we have to do something special to protect it against that. All right, so that's what a race condition is. From an operating system perspective, so how do we handle race conditions? From an operating system perspective, and the one that we're going to focus on here because it's the one most related to us here, we have something called a semaphore. Okay, a semaphore is a special integer whose value is the maximum number of entities that can access this resource at the same time. Typically, this is 1 if we want to provide protected, exclusive access to the resource. So we have a semaphore, we set it to 1. That semaphore effectively acts as the bouncer at the door. Everybody who wants to access that resource, in this case, our integer, has to go through the bouncer. And that bouncer makes sure that only one entity gets access. If the bouncer, if his directive is a 1, his value is 1, he makes sure somehow that only one thing ever can get that resource at any point in time. So what ends up happening is when you acquire the resource, it gets locked. Semaphores act as integers under the hood here. So what ends up happening is that 1 becomes a 0. And when it's a 0, it's locked. And once whichever resource grabbed it has finished doing its thing and it leaves, it gets unlocked. So now that 0 becomes a 1. So the door is unlocked again for somebody else to try to grab the resource. Okay. That's what a semaphore is under the hood. Ultimately, this is something that relies on the ability for instructions to happen atomically on the CPU. Atomically means as if it took a single CPU cycle, like a single instruction on the CPU would take. So if we remember back to last semester when we looked at the Hello World program in Linux, which already used a whole bunch of power tools. Go back to this, call it Hello World Linux assembly. Good enough. This guy right here. And we talked when we were talking about the nature of the CPU on a computer. We said a CPU is kind of like this collection of magic tricks. You know, it was that time where I said, okay, everybody put their hand up. How many of you can do this? Everybody can do that. How many of you could do that? Everybody could do that. You know, do a bunch of other stupid little things like that. And none of those seem all that useful in and of themselves. But we put enough of those little ninja moves together, we can accomplish a task like grabbing a mug or something like that. That's computer programming. Take a whole bunch of little tiny ninja moves that don't seem all that impressive in and of themselves. And if we do those next to each other, a real task might occur. Now, why do we use languages like Java, C#, C++? Go ahead. This would be fun for an hour. But as soon as you start writing something of any sort of substance, for instance, our little program that we're writing right now, which I realize is still probably fairly complex in many of your minds. That's okay. That's right where you should be. All right. If we were to look at the actual core assembly under the hood for just our current program, be thousands of instructions to the CPU, not like 15. All right. So this is not a friendly thing. It's doable by a human. It's not comfortable. We like power tools. Hence, we want those high level languages. Go ahead. It is. Not with online GBD, probably. You could take the code from online GBD. It would be easiest with C and C++. You can look when you use a compiler like GCC, which is GNU C compiler. It allows you to pause it in the middle, like look at the middle step, so you can look at that intermediate code before it linked in all the libraries to create a runnable executable. So the point is there's not a convenient way for us to do it, but it is very possible to do it if you're using traditional compilers from the command line instead of some website type thing. So you can see what your C++ program ultimately turned into in terms of assembly code before it ran it as an executable. Because that is the middle step. Well, I mean, it is an important thing because that is happening every single time we compile a program. That's part of the heavy lifting that these compilers and stuff are doing for us. We write the high level code, somehow it magically becomes an executable. There is stuff that is occurring in the middle there. When we compile it, it goes from high level to low level. This. So what she's talking about is looking at the output of the compilation step before it slams into the linker, which then turns it into an executable. We don't really care about the executable because if we look at it, it's just going to show up as a bunch of weird symbols on the screen and stuff because that's effectively binary. But there is a step in the middle that is viewable, just not conveniently viewable. All right. So in any case, these are what these little magic tricks look like. Now, I would tell you like this magic trick right here, moving something from one place or another to another probably happens atomically, which means it happens in exactly one CPU cycle such that nothing can interrupt it. You can't shave anything off one CPU cycle. That's the smallest thing that can happen on the CPU. But now when we're writing code and we're displaying something and then changing something and you're doing a couple other things in there might be 30 lines of assembly code under the hood there. That's not happening as if it's one thing happening. That's probably taking 30 to 50 CPU cycles. And CPU cycles happen really, really quick. Our CPUs are fast. Okay. But it's probably taking 30 or 50 of those things in there. And if we're not locking the door, we might be in the middle, might be on instruction 11 when somebody else comes in and starts doing stuff to that same resource. So we have to have a way of locking the door so that all the stuff you might want to do occurs as if it is only happening in one CPU cycle. So things like semaphores built into operating systems let us accomplish that. So that's what this thing called the semaphore is. Where did I write that? Race condition, semaphore right here. So we can say this. In Java, we can use the keyword synchronize. Synchronize to protect a block of code from more than one thread accessing it at once. All right. So just another keyword. You create a method, you put the stuff in the method that you want to have happen. That's usually called the critical section if you're talking about this in operating system lingo. So the stuff that you want to have happen atomically, at least uninterruptibly, it's called the critical section. You put that in a method, you mark that method as synchronized. Poof, done. Now it's protected. Okay, we don't have to do a bunch of stuff behind the scenes. So what we would do here is we go back to our code. I go into core. Now, what I would do is I would probably make this field private. Now, by making that field private, it's only accessible inside of this class called core. Okay. Now, that means if I want to have external access to this, I have to kind of have the equivalent of like a getter. So we might create a public method called int, called get count atomic. Is that how you spell that? Atomically? Let's just say yes. Yeah, get count atomically. And maybe this guy returns count. But before he does that, he says count is equal to count plus 1. And this guy needs to be static, this function. All right. And I would probably write this as this dot count is equal to, actually, I wouldn't write it as that. I'd write it as core dot count is equal to core dot count plus 1. But in this case, we wouldn't actually have to type core because we are in a static context, which means we have access to all of the things that are owned by the class we're currently in, which is core. And there's another static thing in here called count. So we would have direct access to it. But I like being explicit. So we're going to say core. I'm going to take your count variable. I want to add 1 to it. Then we're going to go ahead and return that value here. We could also print it out if we wanted to in here, and that would protect the IO, but we'll come back to that here in a second. But we're just going to return it and we'll print it somewhere else. All right. So now I'm going to go and use this right now. I have not put synchronized in here yet. So this guy's called get count atomically. So this just gives us access to that value. And what it does is it adds 1 to it and then returns it. Okay, if we wanted it to return the version of it before we added 1, just return count minus 1 after you've added 1 to it, as opposed to doing that. Why won't that work? Good. Yep. The return keyword, among other things, makes a function immediately end, which means we are never getting to that line. All right, so we need to make sure that we do any of our modifications first. And then if we happen to want to give it the old value as if we hadn't done that yet, we can just return count minus 1, which is just what the value was fraction of a second ago before we changed it. Kind of up to you which version of count you get. Doesn't really matter in our application here. All right. So that's what this guy is, but we're not synchronizing it yet. This is just a normal plain Jane function, just like accessing our variable directly. So a whole bunch of people can call this function at the exact same time and possibly double increment before this value gets returned and printed out. So you might see some values being skipped along the way, depending on the timing of when they hit it. So let's go back to our worker bee. So now instead of getting core.count directly, we're going to say, to get the name of, I copied it, but I changed it. That. So we're going to say core dot get count atomically, even though it's not atomic yet. That's just its name. And that guy is a function. So I'll say core, I want to call your function get count atomically, which adds 1 to count and then returns that value. So this guy will boil down to whatever count currently is plus 1. All right. We won't change it in here because it's being changed inside that function. All right. Keep in mind, we're kind of doing the exact same thing as we were doing before now. We just encapsulated it into this single function inside of core. We're not protecting it at anything at any point right now. So when we run this, we should see a pretty similar experience as we just had. All right, 3-minute warning. I don't remember if I sent an alarm yet. All right, kind of doing the same thing. Obviously, it's hard to tell when we see it spitting across the screen, but there's going to be some repeats and things like that in there. Now, if I go back to, actually, let me do this real quick. I'm going to go to Java thread. And we're just going to put our threads to sleep in between their moves for a second. Well, that's why I just said it out loud. I still have 2 minutes, right? Yeah. 1 minute. My clock says 11:53. It's okay. You guys can always tell me to shut up. I realize it's a problem. All right. So here's the sleep command. And sleep is a static function. So I would say thread.sleep, give it some number of milliseconds. So if I wanted to kind of make this feel a little bit less real time, so I got some, I could view the things a little bit inside of my run method, I could do thread.sleep and then maybe give it 1,000 milliseconds, which is 1 second. Now, when I run this, it should have, oh, it's in an exception. So I got to do a try to do that stuff. Catch. All right. And not do anything with the catch. So now we get a little delay in there so we can view it a little bit as it's going. And if we look at this long enough, we might see a time where you get the same value twice or something like that. We're not protecting it at all. All right. So we'll pause right there. That's our current state. What we want to create now is the ability to protect those values. So actually, I think we just saw that there was a 43 and there was a 45 that came before it. So they actually got different versions of the number. So next time we now have some of the tools we'll need to fake this to give ourselves a way of alternating between our threads with control. All right, so no homework for our Friday, but I'll see everybody there. I will throw this code as it currently stands up on Slack if you want to take a look at it. All right, I'll see everybody on Friday.